Hello everyone. So let's finish up the lab that we started on. We started in our first week. I'm going to start kind of right from explaining things right from the beginning because some people were actually gone and didn't actually get to take their data, and so I'm just going to have to send them some data. For the rest of you, most of you have gotten to the point where you at least have a position versus time curve. So if that's the case, you can skip ahead in the video. I'll put a little marker on the YouTube videos. So that's one of those little yellow dots on the slider bar uh, that will help you skip ahead to the next section. Okay, but starting right from the top, the first thing that we should do is we need to enable a data analysis toolpack. So you can go to File, you can go to Options, you can scroll down to Add, or you can click on Add-ins. Under Manage, you can click on Go, select Analysis Toolpack and Analysis Toolpack VBA, and then hit OK. And now this will enable something that we're going to use to do curve fitting for our data later. Now, once you do this, if you go to the Data menu bar and you've done this properly, there should be this Data Analysis option thing right up here. Okay, cool. So there's that. Now, so here's the lab that we did. Essentially, what all we did was take something and drop it. And so you can see this amazing, beautiful piece of artwork here explaining how a free fall works. So there's we dropped some object and we had a device that basically gave us a record of where that object was every 60th of a second as it fell down. So here's a figure showing you what this would look like. You can see that under free fall, an object that's dropped in every second as it's going down, as it's falling, will pick up speed, and it'll pick up larger and larger. The speed will get larger and larger over time. Right? That's not that surprising. The free fall acceleration is constant in time, so that's really helpful because then we can use the kinematic equations of constant acceleration, or the KECA as I like to call them. And the point of this lab is to measure the free fall acceleration, so the rate at which the object is accelerating as it falls. Okay, so since as you can see here, the KECA, or the kinematic equations at constant acceleration, if you look at the position versus time curve here, you can see for an object with some initial velocity v0 and some undergoing a constant acceleration a, that the position will change as a polynomial in time. Right? This is a quadratic polynomial in time. So that's kind of nice. The velocity, so the velocity will change linearly in time, as this equation shows here. The position will change quadratically in time. Okay, so the whole point of this lab is we have a measurement of y, so we have a record of the position at different timestamps, and we know that each of these timestamps are 1/60th of a second apart because the frequency at which we generated these points was 60 hertz. So every 60th of a second we get a new record of its position. And from that record of its position, we can then calculate some properties. Namely, what we're going to do is we're going to plot the position versus time curve, and by fitting the coefficients of this polynomial here, we'll be able to measure the acceleration, or 1/2 of the acceleration is going to be the coefficient for the quadratic term here. And we'll also be able to measure the free fall acceleration using a numerical calculation of the velocity at each different timestamp. So that's the point. What we're going to do, you can check out the lab manual online for more details on that. Do make sure to look at the lab manual online and read through that especially if you weren't there during lab. I will send you data. You should make sure to read through that lab manual before you send me an email or anything to ask me questions. I'm happy to field questions, but you have to look online first. Now, I'm going to talk about, as I'm going through the data analysis, I'm going to show you some things about Excel that'll be really helpful for you and will make your life better over time. And I'm going to delete this terrible cartoon here because I am so sick of looking at it. Okay, great. So let's start out by getting, so the first thing that everybody did when they had this record of this strip of paper telling, giving a mark where every position was as the object fell, was to number each one of the dots that were made and then measure the position of that dot with respect to some fixed reference point, wherever that was. So since each dot was generated 1/60th of a second apart, I can get a timestamp from each one. Okay, so let's start doing some data analysis. So here, the first thing that I told everybody to measure when they got their strip of paper recording the position where the object was as it was falling was to number each one of the points. So that's what this is here. I started the numbering at 0, and then record or measure using a meter stick the position for each one of the points. So that's what I've done here. And the positions are measured with respect to some, reference point. I chose it to be towards the top, and it really doesn't matter because you can fix this in Excel later anyway. Okay, so this first thing I want to do is just show you how to do some simple Excel exercises that should make your life a bit easier. So if you want to make an Excel function that's going to calculate one column based on some properties of another column, the first thing you have to do is click in that cell and start out with an equals sign. After you type in that equals sign, you can click on some cell, say, to define things in terms of these other cells. So I'm going to click on A2 here. What I want to get is the time for the timestamp for each one of these different data points. And like I said, the points were generated once at a frequency of 60 Hertz, so they're 1/60th of a second apart. So if I take the number of each point, and I multiply that by 1/60, then that will tell me the time, or at least the time differential between each one of these points. Okay, so this here is 0 times 1/60th of a second, and if I go over to the corner here, you see if I move my cursor over to the corner of the cell up until I get this plus sign there, I can double click on that, and this will apply this same function that I used here, fixing things in terms of the cell right to the left of it everywhere down the column. So here this is 0 times 1/60th. Here it's 1 times 1/60th, and then 2 times 1/60th. So this will all the way down to the very bottom one. So this accurately tells us then the time as well as the position that I've measured for each one of these curves. Okay, great. So I have a position and I have a time. So the way that I set up my coordinate axes is maybe it's not wrong, but it's not optimal. So I'm going to first fix that, and I'm going to make a height in centimeters. So I always put the units in closed brackets up on the top of each column. So here, my object started out at position 0 and then finished up at 147. That's fine. That's not technically wrong, but I want to make a different coordinate system where instead I say it started out at, let's just say it started out at 170 centimeters. The overall height doesn't really matter, and went down with time. That way, all I'm doing is flipping around the coordinate system. So I can do that and apply this all the way down. Okay, and so you see here now I'm recording this in terms of height, right? So as the object drops from the start, let's say it starts at 170 centimeters where the first data point was recorded, and the position or the height then gets smaller and smaller as it comes to reach the ground. Okay, good enough. So the overall height, like I said, I shouldn't matter too much because the acceleration is really what we're interested in, and that is independent of the overall height from which the thing is dropped. Okay, so I now have a height and a time column. I'm going to take and plot time, height versus time. So the first thing I'm going to do to make a plot is I'll select the data that I want here, and I can just do that to select the whole column. And then if I hit Control, I can select another one, and I can then I have two. And I can go to Insert and Insert Scatter Chart. So I want to plot a scatter chart always without lines connecting between the things. Always plot scatter points and then add trend lines later. That's the better way to go. Okay, so now I have a plot of height versus time, so you can see as time moves forward, this object is falling, right? The height is dropping in time. All right, so let's work on this plot, because this is completely unacceptable as it is. Let's give it first a good title. So we'll say height versus time for falling object. Great. Okay, now let's do some other things to fix this up. Let's go to, I want to add some things. Formats, chart area. What's going on here? So I want to add chart elements. Let's go. I want to add axes titles. Okay. So on the horizontal axis, I have time, and that's in seconds. I always put the units on every single plot. That's very important. I'm also going to do add a vertical axis title, and I'll call this one height and times. Okay, great. So I have axes, labels, and title. That's absolutely necessary for every single plot that you will make for the entire extent of this class and for all your other physics classes as well. Now, what about a trend line? So I would like to capture this trend and see how this height is changing with time, how this trajectory looks in a more mathematical form. So I'm going to go and add a chart element. I'm going to go to adding a trend line. Okay, so linear. So there's a bunch of different options here, right? There's a bunch of different ones. Let's see, do you think that any of these capture the trend here? Well, linear doesn't appear to even come close to matching those dots. What about exponential? Yeah, definitely not. Linear forecast, that's not what I want, and a moving average is not fitting a trend line at all. So I'm going to go to more trend line options. If I go to then the data, the trend lines options data here, I can see, so as I set up here, right, for these kinematic equations at constant acceleration, that position should be changing quadratically with time. So I can go to polynomial of order 2. That's a fancy way of saying a quadratic fit. And so this, you can see the trend line here captures what's going on in my data quite nicely. So that's really nice. And let's say, let's display the equation on the chart, and we'll put the r squared value on the chart as well. R squared tells you how well, how good the fit is. Okay. So r squared is 1. It'd be nice to throw more significant digits on there, but I'm not going to worry about that right now. Okay, you'll see here I have a trend line fit, and it tells me y versus x, the x-axis. But it would be better to have, instead of x up here, I would prefer to have t, since okay, so now I have height versus time, a falling object. I have properly labeled axes. I have nice looking data points and a trend line, as well as an equation that tells me how good the trend line is. So this is great. This is basically everything that I want for this plot. Okay, so next thing, I want to get a velocity versus time curve as well. Okay, now we don't have any direct measurement of the velocity that we can measure right on our strip of paper. However, what we do have is a bunch of positions and a bunch of different timestamps. And I know that average velocity is equal to change in position over change in time. So if I want to find, say, the average velocity as the object is falling, say the average velocity at the instant, say, of this data point number 1 here, what I could do is take the change in position over the change in time around a symmetric interval around there. So that would look something like this. I can take final position minus initial position divided by final time minus initial time. If I hit enter, that will tell me what the velocity was at that specific point. Okay, now you'll notice, right, I used a symmetric interval. I basically, for point number 1, I want to use the average velocity between point number 0 and point number 2. Okay, that's exactly what I have here. I can hit enter there, and I can, again, go to the corner, double click, and apply this all the way down the row. Okay, so you'll see that this all looks really nice up until this bottom point here, because it's defined in terms of some data point that's not actually there. So I'm just going to delete this one. Okay. Okay, so I have my velocity versus time curve here. I just skipped over in time because I'm just repeating the exact same thing that I did for the height versus time curve. And now I have, so I have all the chart elements that I want there. Axes are labeled. I got a title, and I have the equation as well as the r² value. All right, so as I had said, these coefficients, they match up to these coefficients here in the kinematic equations at constant acceleration. And that's what we use to measure A here, which should be the free fall acceleration due to gravity. And hopefully it looks something like 9.8 meters per second squared once we make our measurements. Well, you can see here from this fit, this looks a lot like v of t equals v0 plus acceleration times time. Right, there's v0, negative 32.8. And the acceleration then is the coefficient of the x-axis term there, which is, in our case, negative 977.4 centimeters per second squared. So it's pretty close to this 980 centimeters per second squared. Note that it's negative just because the object is falling with time, and I've defined that my vertical axis pointing upwards is positive. So the acceleration going as the object goes downwards then is negative. Okay, so the next important question we want to ask is how close exactly are we to 980 centimeters per second squared? So there's a very reasonable question to ask. Is 977.42 close to 980, or is it not close to 980? Well, in order to understand, in order to know that, you need to understand the uncertainties on your measurement. And so the uncertainties here come from several different sources. There's systematic uncertainties involved that we're not going to talk about, but we'll talk about those in later labs. The uncertainties that we're interested in here come from the uncertainty in the fit, the goodness of fit. And the trend line that you put on here is nice. It does curve fitting using and minimizing this r squared, or the difference in the squares between the fit line and the individual points. But what this doesn't give us with the simple trend line is the uncertainties on the coefficients. So for that, we need to use this data analysis tool pack that we already enabled. And so let's take a look at this. So if we go to data analysis, and we'll go to regression and click OK. So now once this regression dialog shows up, you can select input x and y ranges. So I'm going to do that. First, I'm going to use the velocity versus time curve. So I'm going to take as my y axis is the velocity data. Okay, and x is going to come from my time data. Okay. And I'm going to do, if you hit this output range here, you can select exactly where you want the regression information to get dumped into your document. So I'll do that, and I'll select, let's just say that I want it right here. Okay. Now, I don't care about residuals or residual plots or anything like that. I just am going to say I want you to fit the x range that I selected versus the y range that I selected, and I want you to spit it out right there. I'm going to hit OK. So get all of this data here. There's a bunch of stuff in here, and it's not super important. The main thing that I want is right here, so I'll highlight this. Okay, so the main things I want are right here. So you'll see these two values are exactly these coefficients over here on this line. So this is just, and then the second cell here is the standard error on these coefficients. So these are the fit coefficients, the intercept and the linear term, and here's the uncertainty on those measurements. So what we measured then was, let me just draw a text box to make it abundantly clear. So what we measured was not just 977.4, but we measured 977.4 plus or minus 3.2. That's a much more precise measurement. Now we can meaningfully ask the question, and that's okay, so it's in units of centimeters per second squared. So now we can meaningfully ask this question: is 977.4, our measurement, close to 980 centimeters per second squared? Well, once you see that the uncertainties on this measurement are 3.2, plus or minus 3.2, well, 980 falls right within this range here. When you take the central value plus or minus the uncertainty, 980 falls within that. So that means, yes, we did, in fact, measure something that's very close to the accepted value. So that's nice. So now that we've completed the linear fit, I want to do a quadratic fit for the height versus time of the falling object curve, going back to that. So what I have to do is, so I have to put in a second column in order to do that. So I'm going to copy this column, In order to do a quadratic fit, I need to have two columns, one for the linear term and one for the quadratic term. So, well, here, instead of copying, let's just insert another column. So, right-click, insert. And this is going to be my time squared column, and that's in units of seconds squared. And I'm just going to make this equal to this squared. So now, when I do that, select my x and y columns, I'm going to have two x columns to select. It's going to be the linear column and the squared column. So let's do that now. Insert data analysis, regression, okay. Now my y range is, instead of height, so my y range is going to be the height. Okay. And my x range is going to be both the time and the time squared column. Okay. Note that I've selected the same number of data points for both x and y, and I'm going to have the output come right there. Okay, I'll just hit OK, and now I get the same output. Again, there's a bunch of stuff there. The most important things are just right here. Go down to the bottom here, and I will highlight this. Now you see what I have is, so intercept, so this gives me the coefficient, the intercept, the coefficient. Here is the coefficient for the linear term, and here is the coefficient for the x squared term. So here's the 1/2 times the acceleration. Remember, so this is 1/2 times the acceleration was the coefficient for the t squared term, and there's its uncertainty. So if I wanted to get the g we have measured from this, it would be 2 times the coefficient, and I can take 2 times the uncertainty for the uncertainty amount. So just going to copy this and I'll modify it. So according to the velocity versus time curve, we had 977.4 plus or minus 3.2 centimeters per second squared for a free fall acceleration. And according to the position versus height curve, we measured 978.3 plus or minus 0.9 centimeters per second squared. Notice I'm going to the same number of digits for each one, and since the uncertainty is right around at the level of about that first point there, it's right at that first digit, I'm only including one digit in each. So the other digits don't really matter. You know, the 10th decimal place doesn't really matter if your uncertainties start out at the first decimal place. So you can see that this measurement is a lot more precise than the original one was, right? So here, here we had an uncertainty of 3.2 centimeters per second squared. Here the uncertainty is actually less than 1 centimeter per second squared. And the reason for that is that you actually end up compounding the uncertainty in each measurement when you combine those measurements together to get the velocity measurements from the original position measurements. So for nearly all of you, this measurement will be more precise here. Okay, so is 980 does 980 fall within our uncertainties here for this experiment, for the height versus time curve? Well, not quite. 978.3 plus 0.9 would be 979.2. So we're really close, but not quite. So why is that? Well, the reason is just that this one got more precise, so it's less likely that the accepted value would then fall within the range. And but that doesn't mean that we've measured something completely completely unreasonable or anything like that. That's not what it means at all. So the uncertainty just tells you that say this gets into more complicated statistics that we'll talk about in later classes, but this just basically tells you if you got your uncertainties right, there's a 68% chance that the true value falls between this value plus or minus the uncertainty range. So there's a 68% chance, not, so if you extend it out to 2 times the uncertainty width, which would incorporate 980, then the probability goes to like 90%. So there's like a 90% chance that the true value will fall between your measured value and plus or minus 2 times the uncertainty that you measured. So we still measured something very, very reasonable. And we will talk more about uncertainties in later courses or in later labs where we'll get more precise with that. So that is how you do this regression analysis. Oh, one more thing to just repeat and say here. The system, there's 2 different types of errors that factor into an experiment. There's systematic errors and there's statistical errors. Now, this is only taking into account the statistical errors, okay? That's what the regression is able to pick up here. The systematic errors, which come from, say, if my meter stick that I'm using is, say it's off by a little bit from what the true length of a 2-meter stick should actually be. That would be an example of something that obviously the goodness of fit is not going to tell you anything about that. That's because the goodness of fit refers to statistical errors only, and it doesn't take into account the systematic errors. So we'll talk more about systematic errors in more precise detail later. But what you do need to know about that is that these uncertainties are artificially small. The true uncertainty on our measurement is larger than this, and the systematic uncertainties will outweigh the statistical uncertainties by quite a bit in this particular case. Okay, so I hope that makes sense, and now you can finish up the last little bit of that first lab. I want to see, I'll send something around about lab report or lab results expectations, but I do want to see these 2 measurements here of G and the uncertainties, and I want to see your velocity versus time curve and your height versus time curve. That's all going to show up in your final results that you'll submit to me. Okay. Have a nice day, everyone. Bye-bye.